Good morning, students. Today I am going to solve the numericals on heat exchangers. The few numericals on LMTD method first we will solve, and later we will go for the NTU and effectiveness method. Here one thing we already discussed, that one, when we have to apply the LMTD method and when we have to apply the NTU effectiveness method. When the inlet and exit temperatures of both the fluids are given, or inlet and exit temperatures of both the fluids are easily calculated, then we have to use the LMTD method. If the exit temperatures are not available, not easily calculated, then we have to go for the effectiveness NTU method. The first problem, which is on LMTD method, a heat exchanger is required to cool 55,000 kg per hour of alcohol from 66 degrees Celsius to 40 degrees Celsius. Here the hot fluid is to be cooled 66 degrees Celsius to 40 degrees Celsius, and its mass flow rate is 55,000 kg per hour. Using a 40,000 kg per hour of water, this is a cooling water, that is a cold fluid, its mass flow rate is a 40,000 kg per hour, entering at 5 degrees Celsius. Calculate the exit temperature of the water, and second, heat transfer. Third one, surface area required for parallel flow type and counter flow type. Take overall heat transfer coefficient U is equal to 580 watt per meter square Kelvin. Cp of alcohol is equal to 3760 joule per kg Kelvin. Cp of water 4180 joule per kg Kelvin. Sometimes Cp of water may not be available. That 4170, that we have to 4180 we have to take as a common. And here the given data we will write first. The mass flow rate of the hot fluid 55,000 kg per hour divided by 3,600 we have to take in terms of kg per second. 40,000 kg per hour, again here we have to divide with the 3,600. Then inlet temperature of the hot fluid 66 degrees Celsius, and inlet temperature of the cold fluid 5 degrees Celsius, and outlet temperature of the hot fluid is 40 degrees Celsius, and outlet temperature of the cold fluid is not given, but here we can calculate easily by using the three temperatures. That by energy equation, that is heat lost by the hot fluid is equal to heat gained by the cold fluid, that is heat lost by alcohol is equal to heat gained by water. Here that can be given as mHCpH Thi minus Th0, that is equal to mCCpC Tc0 minus Tci. And in this one, mass flow rate of the hot fluid 55,000 divided by 3,600 kg per second. Cph is 3760 and Thi 66, Th0 40,000 mc 40,000 kg per hour, and divided by 3,600, that will be kg per second. Its specific heat is 4180, and Tco we have to find out, outlet temperature of the cold fluid, and inlet temperature of the cold fluid is 5 degrees Celsius. From this one we can have the outlet temperature as a Tc0 is equal to 37.16 degrees Celsius. Exit temperature of water. Then second one, heat transfer. The heat transfer given by energy equation as a mHCpH Thi Th0, the heat lost by the hot fluid. The similar way we can calculate by using the heat gained by the cold fluid also. Okay, here easily we can find out 55,000 by 3,600, 3760, 66 minus 40. This we can have the 1493.55 kilowatt. Okay, then third one, surface area for parallel flow heat exchanger. To find the surface area for parallel flow heat exchanger, we have to use the heat exchanger heat transfer equation, that is a Q is equal to UA delta T LMTD. From that A we have to determine For that, Q we already calculated as 1493.55 kilowatt, and U it is given overall heat transfer coefficient. A we have to find, and then LMTD for the parallel flow heat exchanger, that we can determine. Already we know that LMTD equation as LMTD is equal to delta T naught minus delta TL by ln of delta T naught by delta TL. Okay, this notation delta Ti minus delta T naught by delta Ti by delta T naught also we can take, but here the similar notation is taken. Thi minus Tci, this delta T naught is equal to at the inlet for the parallel flow heat exchanger, and for counter flow heat exchanger it is for parallel flow heat exchanger outlet temperature difference Th naught minus Tc naught divided by this Thi minus Tci by Th naught minus Tc naught, ln of this one term. If you all the terms you know, all the temperatures, then if you substitute 66 minus 5, 40 minus 37.16, 66.5 ln of 66.5 by 40 minus 37.16. This will have the 18.96 degrees Celsius. Then LMTD we are having the Q is equal to UA delta T LMTD. Then Q 14.93 into 10 raised to 3, that is equal to 580. U is given, area we have to calculate. Then 18.96 delta T LMTD. Then area will have 135.8 meter square. The similarly surface area for counterflow heat exchanger. For that LMTD equation remains same, delta T naught minus delta TL by ln of delta T naught by delta TL. But here delta T naught is equal to inlet temperature of the, this one is Thi minus Tc naught. Thi minus Tc naught, that is the inlet temperature of the hot fluid minus outlet temperature of the cold fluid, and delta TL is equal to Th naught minus Tci. Okay, where the exit temperature of the hot fluid is there, there the inlet temperature of the cold fluid is there. Then ln of Thi minus Tc naught by Th naught minus Tci. From this we can write LMTD by all the parameters we know, all the temperatures, we can find out the LMTD as 31.82 degrees Celsius. Then Q is equal to UA LMTD. Then this Q already we have 1493.55 kilowatt. Then watt, in terms of watt we will take 580 overall heat transfer coefficient, and A is area, and this one is the LMTD temperature. Okay, then from that area we will get 80.9 meter square. 80.9 meter square. Here the area, surface area what we got, that is less than that of the parallel flow heat exchanger. From this we can see that one less area is required for the counter flow heat exchanger than the parallel flow heat exchanger. Okay, similarly we will go for the next problem. In a double pipe heat exchanger, hot oil with a capacity rate of 2500 watt per Kelvin flows and enters at 360 degrees Celsius and leaves at 300 degrees Celsius. Cold fluid enters at 30 degrees Celsius and leaves at 200 degrees Celsius. If the overall heat transfer coefficient is 800 watt per meter square, determine heat exchanger area for parallel flow and counter flow heat exchanger. This is also similar numericals. Area of the heat exchanger we have to find out for the parallel and counter flow heat exchanger. First we will write that is what are the given data are there. Here a capacity rate is given. Capacity rate, that is capacity rate of the hot fluid will be CH, that is a product of the mass flow rate and the specific heat MHCpH is, that is a capacity rate, that is 2500. Then here that hot fluid inlet temperature is given 360 degrees Celsius, hot fluid outlet temperature 300 degrees Celsius, cold fluid inlet temperature 30 and cold fluid outlet temperature 200 degrees Celsius, and overall heat transfer coefficient U is given 800 watt per meter square Kelvin. Then here the already we know that CH is equal to MHCpH, that is 2500. Then Q is equal to CH Thi minus Th naught, that is equal to, this is a heat lost by the hot fluid, 2500, it is a specific, it is given. Inlet temperature is 360, outlet is 300. Then from that, the heat transfer rate will get. As if you have the heat transfer rate, if you use in the heat exchanger heat transfer equation, then by the LMTD method, we can have the area from that one. If you know the heat transfer rate and overall heat transfer coefficient and LMTD, then we can find out the area. Then LMTD that can be given as a delta T naught minus delta TL by ln of delta T naught by delta TL. For parallel flow heat exchanger, delta T naught is THI minus TCI, that we can write 360 minus 30 is 330. Then delta TL is TH naught minus TC naught, that is equal to 300 minus 200, that is 100 degrees Celsius. Then LMTD that we can find out 330 minus 100 by ln of 330 by 100, that will give the 192.64 degrees Celsius. Then already we know that Q is equal to UA LMTD. Then area can be Q by UA LMTD. Then 150 into 10 raised to 3 kilowatt it is. Then 800 U LMTD 192.64, we are going to get the 0.973 meter square area. Similarly, for counterflow heat exchanger, LMTD, that same equation, delta T naught minus delta TL by ln of delta T naught by delta TL. Then this can be written as THI minus TC naught and TH naught minus TCI by ln of THI minus TC naught and TH naught minus TCI. Then by substituting all the temperatures, we are going to get the LMTD as 210.22 degrees Celsius. Then area can be calculated by using this one Q by UA LMTD. That is 150 into 10 raised to 3 by 800. Overall heat transfer coefficient, LMTD is 210.22. Then it is 0.892 meter square. Then another problem we will take that one. This is somewhat different. Oil at 100 degrees Celsius, Cp is equal to 3.6 kilojoule per kg Kelvin, flows at a rate of 30,000 kg per hour. Oil at a temperature of 100 degrees Celsius. Okay, it flows at a rate of 30,000 kg per hour and enters a parallel flow heat exchanger. Parallel flow heat exchanger, it is a hot fluid. Okay, as here you can see that cooling water with Cp is equal to 4.2 kilojoule per kg Kelvin enters heat exchanger at 10 degrees Celsius at the rate of 50,000 kg per hour. The heat transfer area is 10 meter square and U, that is overall heat transfer coefficient, is 1000 watt per meter square Kelvin. Calculate outlet temperature of oil and water. Okay, here outlet temperature of the oil and water is asked. Here only inlet temperature of the cold and hot fluids are given, its specific heats are given, the flow rates are given, and also but area is given, overall heat transfer coefficient is given. But only thing is that one outlet temperatures are asked. Whenever outlet temperatures of the both the fluids are not given, are not calculated easily, in this equation it is not easily you can calculate the outlet temperature. That's why we have to use the effectiveness NTU method. Whenever outlet temperatures are not given, are not calculated easily, then we have to use the effectiveness NTU method. Then for that NTU method we have to use this numerical. For that first thing, whatever the in the NTU method is there, to find out the product of the mass flow rate and the specific heat, that is capacity rate for the hot fluid and the cold fluid. To find out the C min and C max, it is very important. For that, capacity rate or a product of the mass flow rate of the cold fluid and the its specific heat, that is a 50,000 by 3,600 into 4.2 into 10 raised to 3 is equal to 58,333.3. Then CH is equal to MH CPH, then that is equal to 30,000 by 3,600, then that is equal to into 3.6 into 10 raised to 3 its specific heat, then that will be 30,000. And from this one, these two values, the maximum value is 58,333. Therefore, that is the Cmax. Therefore, Cmax is equal to 58,333.3. C mean is 30,000. Okay, from this we will get C max and C min. Then C, the ratio of the minimum to the maximum, C min by C max, C we can find out, which is to be used in the its effectiveness equation. That C is the C min by C max, that is the 30,000 by 58,333, that 0.514, that is equal to C. Then NTU, number of transfer units, NTU or N, that can be given as UA by C min. U is 1000, area is 10 by 30,000, that is a 0.333, is we are going to get the NTU. Effectiveness is equal to, this equation we can have from the data handbook, or you can remember 1 minus e raised to minus n, 1 plus c by 1 plus c. Already we have discussed, we have derived. Then this can also we can have from the data handbook, that is effectiveness is equal to 1 minus exponential minus n 1 plus c by 1 plus c. Then this equation we can use and substitute all the terms. N is minus 0.333, 1 plus 0.514 by 1 plus 514. From this effectiveness we can have 0.2615. Effectiveness is equal to 0.2615. Then effectiveness equation in terms of the temperatures, already we have taken, that is that whatever the Q by Q max, actual heat transfer to the maximum heat transfer, that can be given either heat lost by the hot fluid to the heat gained by the cold fluid. Heat lost by the hot fluid, that can be written as effectiveness is equal to CH THI minus TH naught by C min into THI minus TCI. All the terms we know that one. Here we can substitute. Then effectiveness term already we know, only TH naught we don't know. Then TH naught we can find out. TH naught is 76.465 degrees Celsius, outlet temperature of the oil. Outlet temperature of the oil is 76.465. And also effectiveness can be given as a heat gained by the cold fluid. That heat gained by the cold fluid, that can be given as Cc into Tc naught minus Tci by C min into Thi minus Tci. This is the effectiveness equation in terms of the temperatures, and that equation in terms of the NTU and the C, that is the C min to the C max ratio. In terms of that, we can write that effectiveness equation, what I have taken from the data handbook. Then here also if you substitute, this is Cc and the C min, then Tc naught is unknown, Tc naught minus 10, that is Tci, 100 minus 10, Thi minus Tci. Then already 0.2615, this we know that as effectiveness. Then effectiveness from that one, Tc naught we can find as a 22.1 degrees Celsius outlet temperature of the water. Okay, like this we can find out the outlet and inlet temperatures of the hot and cold fluid by using this effectiveness method. Okay, then some other numericals based on this effectiveness method, or some cross flow heat exchangers, those I will discuss in the next class.